Hello pre-calc honors students, here we are with our last video of the year, MT 18.5, Implicit Differentiation. You can see just how swift this implicit differentiation is. If we got something like y squared plus x squared equals 9, that's a circle, and we can come up with the equation of the derivative just by taking the derivative of both sides with respect to x right away. Now, I'm going to go carefully into this, but basically first let's see how this works on a circle in GeoGebra. Here we go. There's my circle, x squared plus y squared equals 9. Here's a point on the circle, and I had GeoGebra put in the tangent line. Notice what you got to see bouncing back and forth there is the x and the y coordinate of A. And notice how the implicit differentiation came up with negative x over A. If you look at negative x over y in this case, negative x over y, it keeps matching the slope of the tangent line. Now you can see why that happens though too, because if you draw this line coming out here like this segment, from A out to this point, what's the slope of this? But y over x. And the perpendicular slope then will be negative x over y. So that's a geometric way we could have come up with the equation for the tangent line. But notice in this case that we are actually defining the slope, the derivative, in terms of both x and y. That's another aspect of implicit differentiation. Okay, first let's compare this with how we would have done it the old way. Okay, the old way was explicit differentiation. That is, we've got to get y as a function of x. So y squared equals 9 minus x squared. So y equals plus or minus the square root of 9 minus x squared. So that's the plus half. Remember, y equals the square root of 9 minus x squared is the top of the circle. And the opposite of the square root of 9 minus x squared, that's the bottom of the circle. So, how do we take the derivative of each here? Let's look at y equals the square root of 9 minus x squared. Now we see that the derivative of the other one will just be the exact opposite. So we can do our derivative with our special trick, 1 over 2 square root of 9 minus x squared. But then you got to multiply it by the derivative of the inner function, which is negative 2x. So you get the derivative is negative x over the square root of 9 minus x squared. And then you realize square root of 9 minus x squared is y squared, is the square root of y squared, which is y. So there's your derivative of negative x over y. So here's the explicit form, the derivative explicitly in terms of x. Here's the derivative in terms of both x and y. And we're going to talk about the technique of doing implicit differentiation now to get at these a lot more efficiently. We're going to start with this example of xy squared minus x cubed y equals 6. This is very hard to solve for explicitly. Xy squared minus x cubed y equals 6. Now I suppose one could say, oh, but you can think of this as y squared times x plus negative x cubed times y plus negative 6 equals 0, and put it into the quadratic formula and solve for y. The opposite of b, so that's x cubed plus or minus the square root of b squared, so that's x to the 6 minus 4ac, so it's minus 24, a which is x, times c which is negative 6, I got that right, all over twice a, 2x. Well, be my guest, that is a bear to take the derivative of. So instead, we've developed this technique of doing it implicitly. Here's just an illustration of where you might apply for this when you're taking calculus next year, and then the multivariate beyond that for doing the tangent planes to three-dimensional surfaces. So let's find this dy dx if xy squared minus x cubed y equals 6. So we start out by taking the derivative of both sides with respect to x. We're going to use this d over d notation. And notice I put it on the left. I'm not multiplying both sides by d over dx. I'm taking the derivative of the left side with respect to x and the derivative of the right side with respect to x. We can distribute the derivative idea over subtraction. So the derivative with respect to x of xy squared minus the derivative with respect to x of x cubed y equals the derivative with respect to x of 6 is just 0. Now I've got to use the product rule on each of these. So we're going to leave x alone and take the derivative with respect to x of y squared, plus now leave the y alone, or leave the second part alone, take the derivative with respect to x of x times y squared. And we're going to split up the other side too. So it's going to be x cubed times the derivative with respect to x of y plus the derivative with respect to x of x cubed times, then leave the y alone. That's just the product rule. Now, here comes the tricky part. You've got x times the derivative with respect to x of y squared, which is 2y, but then you have to multiply by the derivative of the inner function. In this case, y is acting like an inner function. We're taking the derivative with respect to x, plus the derivative with respect to x of x is just 1 times y squared, minus x cubed times the derivative with respect to x of y is just our dy dx. That's the thing we're looking for. And I'm distributing this, the plus and negative over this, minus the derivative with respect to x of x cubed is 3x squared, and then I leave the y alone. Notice this pattern of the dy dx just shows up here and here, where I actually took a derivative of the function y. In the other parts, when I took the derivative of a function involving x, whether it's x cubed or x, there's no dy dx left over. And this whole thing equals 0. Now for our next step, we start simplifying this. Let's write it over again. 2xy dy dx plus y squared minus x cubed dy dx minus 3x squared y equals 0. What we aim for now is focus on the terms that contain the dy dx. And these are going to stay on this side of the equation, so that you get 2xy minus x cubed times the quantity dy dx. Those terms stay on the left. I'm going to move these to the other side, 3x squared y minus y squared. And now I divide both sides by the coefficient on dy dx. 3x squared y minus y squared over 2xy minus x cubed. Now, I suppose out of the top we could factor out a y, leaving behind 3x squared minus y. And out of the top you could take out an x, leaving 2y minus x squared. But it doesn't reduce at all, so I would accept either. Now here's your check on the TI-89. It's actually called Imp-Diff, and you can look it up in the catalog. Imp-Diff, and you actually put in the whole equation, not just the function, the thing after the f of x equals, but the whole thing. And that was xy squared minus x cubed y, x times y raised to the 2 minus x raised to the 3rd times y. And don't forget that it's equal to 6. You got to put that in there, equals 6. Comma x, comma y. You actually specify 2 variables. And let's see what the TI-89 comes up with. Okay, Imp-Diff only has one f in it. There you go. And this is what Imp-Diff tells me. Negative 3x squared minus y times y over x times x squared minus 2y. Well, you see you got the bottom switch there. That negative comes up on the top there. And so they do agree. Check. Now what you have written out in your book here is actually, Mr. Bergen did this a long time ago. It's the same thing I did, just typed up. Now, the point 13 lies on that curve. What is the equation of the tangent line at the point 13? The slope is, for 13, you got to put 1 and 3 both in the equation. And so, let's look at our equation again. We had dy dx equals y times y minus 3x squared all over x times 2y minus x squared. If you put in the point 1 comma 3, that's x is 1 and y is 3. 3 times 3 minus 3 times 1 squared over 1 times 2 times 3 minus 1 squared. We get 3 times 0 all over 6 minus 5, so you get 0. So basically it's horizontal line. The slope equals 0, so you get y minus y1. 3 equals slope 0 times x minus 1, so y equals 3. Now we're going to look for where's the tangent line vertical and where's the tangent line horizontal. First of all, for vertical, this means the derivative dy dx is undefined. That's when you have a vertical tangent line. Vertical slope of the tangent line. So to get it to be undefined, we have to set the denominator equal to 0. So x times 2y minus x squared equals 0. So either x equals 0 or 2y minus x squared equals 0, 2y equals x squared. Well, let's look back at our original equation, which was x squared y, xy squared minus x cubed y equals 6, x y squared, oh gosh, xy squared minus x cubed y equals 6. And if you set x equal to 0, basically you get z equals 6, so we get no answers from that. If we set y equal to x squared over 2, now we get x times x squared over 2 squared minus x cubed times y, which is x squared over 2. Set that equal to 6. I'm getting x to the 5th over 4 minus x to the 5th over 2 equals 6. Let's multiply through by 4 to get x to the 5th minus 2x to the 5th equals 24, or basically negative x to the 5th equals 24, or x to the 5th equals negative 24, x equals the 5th root of negative 24, which does exist. And let's see what the calculator comes up with. And this ends up being approximately negative 1.89, where we made a vertical tangent line. Okay? Now for horizontal tangent lines, for the horizontal tangent lines to this function, we want to know when the derivative equals 0, so we're going to set the numerator equal to 0. And the numerator of our derivative was y times y minus 3x squared. Y times y minus 3x squared, and set that equal to 0. So that either means y equals 0 or y equals 3x squared. Well, again, looking at our original function of xy squared minus x cubed y equals 6, if we set y equal to 0, that leads to 0 equals 6. There's no solution there. But if we set y equal to this other one, we have x times 3x squared squared. This sounds familiar. Minus x cubed times y, which is 3x squared, equal to 6. And we get 9x to the 5th minus 3x to the 5th equals 6, or 6x to the 5th equals 6, or x to the 5th equals 1, x equals 1. And when x equals 1, that means 1 times y squared minus 1 cubed times y equals 6. Y squared minus y minus 6 equals 0. This gives us two answers. Y minus 3 times y plus 2 equals 0. So y equals 3 or y equals negative 2. And we end up then with a point at 1 comma 3 and 1 comma negative 2, where we have horizontal tangent lines. Now when I actually looked at this though, there's the solutions for the vertical and horizontal tangent lines. 1, 3 and 1, negative 2. Right? When I actually look at this, there's the 1, 3. There's our horizontal tangent line at 1, 3. The slope definitely equals 0. And here, somewhere in here is this point at negative 5th root of, what was that? We came up with negative 5th root of 24, and you can plug it in to figure out what the y value is. But that's where you get a vertical tangent line. I'm sorry, was it 32 or 24? Negative 1.8 or so. There's your vertical tangent line. But let's look at 1, negative 2, which is a point on the graph, but this does not look like a horizontal tangent line. In fact, let's actually sub back into dy dx and see what we get for the point 1, negative 2. Remember the formula for dy dx? Way back here, it was, let's cut this out. Paste in here. And let's see what happens when we put in 1, negative 2. Negative 2 for y, negative 2 for y, 1 for x, over 1 for x, negative 2 for y, 1 for x. And we get negative 2 times negative 2 minus 3 is negative 5, over 1 times negative 4 minus 1 is negative 5. I'm getting a slope of negative, it should be positive 2. How do I do this? Negative 2 minus 1 is negative 5. That's right. 1, negative 2, 1 for x, negative 2 for y, negative 4 minus is negative 5. Y is negative 2 minus x is minus 3. That's negative 5. That should cancel. Y is negative. I'm getting a slope of negative 2. At 1, negative 2, I'm not getting a horizontal slope at all. I'm getting a slope of, well, this one says it should be a slope of negative 2, and the graph says a slope of 2. So something's fishy here, that either GeoGebra's graphing this wrong, but it's clearly we've shown that 1, negative 2, even though it might be a solution, it does not create the slope of 0 we were looking for. So I'm going to throw that one out. Let me just check one more time. Now here's another way you can check it on your calculator. If you want to check a specific value of an implicit differentiation, check out this. You go imp diff. In this case, we have that same function you had before, so you can call that up from what you had before. And that was xy squared minus x squared cubed y. Xy squared minus x cubed y equals 6, comma x, comma y. Put the big with symbol down. You can put down the two conditions. X equals 1 and y equals negative 2. And let's see what it says. Yeah, the T89 says a slope equal to 2. So that checks out with our graph. That definitely looks like a slope equal to 2. I think I perhaps didn't copy everything correctly on our derivative here. Let's look back over here. Dy dx is y times y minus 3x squared over x times 2y minus x squared. This is saying y times 3x minus y, 3x squared minus y, and x times 2y minus x squared. Yeah, I'm missing a negative sign on this one. Sorry, it didn't show up on here because it worked out to be 0. So yeah, this is fine. 1, negative 2, we do end up with a slope of 2. Okay. Now let's do another one. Consider the implicit equation below. Calculate dy dx. So the derivative of sine of xy plus x squared equals 3y to the fourth. Took the derivative with respect to x of both sides. So now it's the derivative with respect to x of the sine of xy plus the derivative with respect to x of x squared equals the derivative of 3y to the fourth. Well, that's going to be 3 times 4y to the third dy dx. Now this side's going to be a little more complicated. The derivative of the sine is the cosine. We leave the inner function alone, and then outside of it we have to take the derivative of the inner function. Here's the dinner. X times dy dx plus, now take the derivative of x, which is 1, and leave the y alone. The derivative with respect to x of x squared is just 2x. On this side we have 12y cubed dy dx. So the key here is identifying where your unknowns are, where your dy dx is, and it's here and here. And I want to get those on one side and all the terms that don't contain them on the other. So that means expanding out first. So x cosine xy times dy dx plus y times the cosine of xy plus 2x equals 12y cubed dy dx. So now you want to get the dy dx terms on one side. So it's x cosine xy minus 12y cubed times dy dx, and all the terms that don't have that on the other. So that's going to be minus 2x minus y cosine xy, and then divide by the coefficient on dy dx. So we get negative 2x minus y cosine xy all over x cosine xy minus 12y cubed. I don't see any easy ways to factor this. So let's do our TI-89 check. Impdiff sine, left parentheses, x times y. If you just say xy, you might try and look for a variable named xy. Plus x raised to the 2 equals 3y raised to the 4th, comma x, comma y. And let's see what impdiff says. And impdiff says negative quantity cosine, negative quantity cosine of x times y plus 2x all over x cosine of x times y minus 12y cubed. Checks with what we got. Okay. Yep, and there's this is off of Wolfram Alpha. Because GeoGebra wouldn't graph it for me. A real flange out. It's my 11th birthday. No, 11th video. Maybe my 11th birthday will come up soon. Thanks for a great year, people.